This is the second part of a topic on trig equation solving. There is a first part that deals with some elementary trig equations. In this lesson, I'm going to cover three examples that are more complex. Here's the first one. Sine x minus 1 equals cos x. Now, what makes this difficult is that I've got both sine and cos and no clear identity to substitute. However, I do know things about the squares of these functions. So I'm going to square both sides of the equations, which is legitimate and remains equal because I'm doing the same operation on both sides. This is a binomial square that I'm going to expand on the left, and there's the result on the right. I'm going to write cos squared. Now, hopefully the idea occurs to you of something you can replace. You may want to pause and try it and then come back and rejoin me. The substitution is cos squared is 1 minus sine squared. You'll notice that now the equation is completely written in terms of sine. Let's gather all the terms to one side of the equation. And I have a 1 on each side of the equation that's going to cancel. I'm going to factor. I always want to write these factored and equal to 0. The remainder is sine x minus 1. This 2 has no bearing on the solutions. If I divide the equation by 2, it will cancel. So my roots involve sine x equaling 0 or sine x equaling 1. These are quadrantal angles. Sine x is 0 when x is 0 or pi. Sine x is 1 when x equals pi by 2 only, not 3 pi by 2. That would be negative 1. Okay, now we can check our solutions on a graphing calculator, and maybe I'll take a moment to do that for this one. Let's have a look here. I have got sine x minus 1 minus cos x. So I've done it similarly to how I did in the last lesson. I've moved all the terms to one side, set it equal to 0. Now, sine has a range between 1 and negative 1. Cos has a range between 1 and negative 1. And I'm subtracting 1. So I'm thinking at most I could go between maybe 3 and negative 3 for my range value. So let's use that and see how we do. And I'm going to go 0 to 2 pi for my conditional answer. And let's see how we do. It's not going to look like a normal sinusoid probably, not when you have combined terms. So I'm trying to find out where this equals 0. And it looks like I have two values right here and right here. Now, x equals 0 doesn't seem to represent on here. So I'm wondering if there might be an error. Let's go back to the original equation and check it. If I had sine 0 minus 1, and I compare to cos 0. Cos 0 is 1. Sine 0 is actually 0 minus 1. So I get negative 1 equals 1, which is an extraneous root. Extraneous root. So the problem was that I squared things on both sides, and squaring negatives makes them positive. So I actually have to reject this root. It's always a good idea to check your roots, especially on complex equations. Let's move on to another one. Now in this case, I've got secant and tangent, and they're different than each other. I'm going to take advantage of a Pythagorean identity that tangent squared plus 1 equals secant squared theta. And this has been covered in the past, and you can look that up if you need to under Pythagorean, not theorem, Pythagorean identity. So my secant squared gets rewritten as tan squared x and 1. Leave tan x alone. Bring 5 to the left side of the equation and make it equal to 0. I'm going to expand, and I can see that I have a quadratic trig relationship. So I've got tangent squared, I've got tangent. This is 2 minus 5, so minus 3. If this is difficult for you to view and see what to do, try something like this. Let a equal tan x. I now have 2a squared plus a minus 3 equals 0, a trinomial quadratic that you've practiced and factored many times in the past. And I'm going to write this with a 2a and an a and a plus 3 and a minus 1. You can expand that and make sure that that factors, or expands out rather. And now I'm going to substitute back the fact that a equals 10x. So 2 10x and 3, and 10x minus 1 equals 0, from which, because I have factors equal to 0, I write 10x is negative 3 halves, or 10x is 1. Now, negative 3 halves is not a special angle. 10x equals 1 is a special angle, and the reference is pi by 4, and it's in quadrant 1 and quadrant 3. So two of my roots are pi by 4 and 5 pi by 4, and I know those values exactly. These ones I don't know exactly, so I'm going to write it as arctangent of negative 3 halves, the ratio, to get the angles. Now, arctan is negative in quadrants 2 and quadrants 4. When I use my calculator, it is going to give me a negative angle representing quadrant 2. That's my prediction. Arctangent negative 3 divide 2, close bracket, and sure enough, negative 9828. Negative 0.9828. So that's a quadrant 4 angle. Add 2 pi to find the positive conditional angle within 0 to 2 pi, which is the normal domain restriction, 0 to 2 pi. 5.30, that was 5.300 for that matter, and the other value is in quadrant 2, so it is pi subtract 0.9828 to form an angle in quadrant 2. So let's try that. Pi minus 0.9828, and I get 2.159. 2.159. So 4 answers, 2 of them exact, 2 of them approximate, and that's how you do a quadratic trig equation. I got one more to cover with you, and that's right here. The thing that makes this problem difficult is that 3. The period of this function is 2 pi divided by 3. So I'm going to sketch something out to help you visualize what's going on here. I'm going to make some axes, and I'm going to draw a cosine graph. So cosine would normally look like this up to 2 pi, but it's 2 pi by 3. So I'm actually going to have another one of these and another one of these before I actually get to 2 pi. You notice that I have 3 cycles. It's kind of a rough, crude sketch, but does the job. Now, I'll isolate to get 1/4, and I'm going to rewrite this as cos theta equals 1/4, because 3x is really representing, I'm just going to make some room here, 3x is really representing an angle. Now, 1/4 is a ratio that we don't know the exact value of, and it is graphically like this. Now you'll notice that there are 1, 2 answers. That's quadrant 1 and quadrant 4. But there are 2 more answers representing a quadrant 1 and 4 coterminal value, and 2 more answers again representing quadrant 1 and 4 that are again coterminal. So here's what I'm going to do. I'm going to say theta is arc cos of 1/4, and using my calculator, I know that that's 1.318 radians. Now, that's the angle that would be in quadrant 1. The other angle is in quadrant 4, and it's going to be 4.965 radians. Okay, so what I've done is 2 pi minus this reference angle, 2 pi minus 1.318. Now that's what theta is, what some generic angle is, but I don't actually have theta. I have 3x equal to that. And I have coterminal values. Same over here. I've got 3x, equals 4.965 plus coterminal values. So when I actually solve for x, I need to remove 3 by division. So I'm going to divide this term, and I'm going to divide the coterminal by 3. And you'll notice that now I'm showing the period, 2 pi by 3 n times. Over here, I'm going to have that decimal divided by 3, and again, 2 pi by 3. Now, when n equals 0, I get the roots that I had before, 0.439 and 1.655, because n0 here causes this term to drop out. When n is 1, this is representing the second cycle, and I'm adding 2 pi by 3. So x is now 0.439 plus 2 pi by 3, which is equal to 2.53. Now on that basis, see if you can get the rest of this and then come back and rejoin me and see if your answers match up with mine. Alright, I've finished off the rest of the question. Here are the two roots that we had by taking the first and fourth quadrant and dividing by 3. And here are the additional roots that I get from the decimal 439 root with a single 2 pi by 3 and then two sets of 2 pi by 3 when n is 1 and 2. And the same idea applied to the 1.65 angle with 1 2 pi by 3 and two sets of 2 pi by 3 representing the 6 angles for this question. You may want to review this one again and try it out one more time on your own after having seen this. It's kind of tricky and confusing. Good luck with the assignment.